Hello and welcome. Thursday morning, time to do some more geo homework. Might as well rise and shine, get your geo homework out of the way. I'm going to do 4 of your problems from the problem set you have, your asynchronous problem set today. Check your comments on the exit ticket if I've gotten to it last night. Then you have some feedback on how you did 2 of these problems, actually. And if you haven't gotten feedback yet, please look out for it. I'm going to do this right afterwards, ready feedback on your exit ticket. Okay, so you did your exit ticket yesterday. We did section 2.5, day 2. We're over here. We're on Thursday. So reminders, we have this website, right, the GOA Fall Schedule 2020. This is linked to directly in Google Classroom. It's at the top of Google Classroom and all the helpful links that we have there. And you get all the problems you have to do. Okay, so you're going to do 1 classroom exercise today. That's going to be filling out another table connecting number of sides to interior angle sum to exterior angles, each exterior angle of a regular polygon at least. So you kind of did something similar to that in your written exercises in day 1. Day 2, also, we have a few written exercises. We're basically going to do the rest of the B-level problems. So you're going to do all B-level problems in this section, which that's kind of cool. You actually get to do all the problems here. We have time to do that. And then finally, you're going to do the self-test. Self-test, page 86, numbers 1 through 7, and that's self-test 2. We didn't do self-test 1, so maybe you're going back and checking, do I know how to do self-test 1, 2? Because we have a quiz on all that stuff that gets covered. Self-test 1 and self-test 2 covers sections 2.1 to 2.5, which is going to be our quiz next week. And that's scheduled for now on Wednesday of next week. We'll have a 2.1 to 2.5 quiz. And that's really the core stuff that we got to focus on here in chapter 2, because we got to know it going forward. Okay, so that's why we're really honing in on those 5 sections. Okay, so that's what you're going to be studying that over the next week. Anywho, we're not done yet. Kind of reviewing section 2.5. Oops, should be 2.5, day 2, the angles of a polygon. So that's going to be your final new day of homework, right? Get in the section one time, then it's all about review afterwards. So I'm going to go through some of these problems with you. I want to do through 4 problems, just 15, 16, 17, 22. Again, the rest of the problems, they're on the spreadsheet I was just showing to you. But I'm going to go through these 4 because they're a little trickier. First things first, numbers 15 and number 16, we'll do those a little bit together. I'm not going to do the whole thing with you because these were actually on the exit ticket yesterday, which I wrote you feedback here. So I think I could talk through a word problem like this. If you're having trouble with word problems, I can help you turn this into an equation right now. But just know that I've been emailing this out. Here's my exit ticket explained right here. Okay, so the answers to these have already been shared with you. They're on the exit ticket explains. So you're checking out this Google Doc to get feedback on some of the problems you have here. So let me slow it down for a second. Look, this is number 15 right here. So you've already done number 15 on the exit ticket. Hopefully you got it right. The answer is going to be 10 sides. But I want to make sure you know how to read a word problem like this and come up with an equation. So that's what I'll go over for number 15. Number 16 is the same deal. It's a word problem. Again, you have words. What are the words you look for? How does that change to math? How does it change to equation, right? I mean, math is word problems, right? So sometimes how do you change to math? How do you change it to an equation? How do you change it to a math sentence? A math sentence is an equation is a type of math sentence you can write. And this is definitely a math sentence because we see this word is right here. We see the words is, we know it's going to be an equation, okay? So let's just get them both set up together to make sure that we know them. Number 15, shall we? Let's dive in. All right, number 15 says the sum of the measures of the interior angles of a polygon is 4 times the sum of the measures of its exterior angles. 1 angle at each vertex. There we go, 1 angle at each vertex. So we know the number of sides, we're going to have the same amount of sides as we have angles, right? Interior angles of the shape. And it says 1 angle at each vertex. That means 1 set, right? 1 set means 1 angle at each vertex going in 1 direction. Anyways, how many sides does the polygon have? Okay, is this a regular polygon? Well, we don't know. It doesn't say whether it's regular or not. Hold on, my dog just opened the door. I'm going to go close this. All right, now I'm back on it. So we don't know if it's regular or not, but we do have some things that we have formulas for. Okay, the sum of the measures of the interior angles of a polygon. So I want to underline that, the sum of the measures of the interior angles of a polygon. Do we have a formula just for that for any convex polygon? Like anything? Right, this means I think they're getting at convex polygons at least here. So they're not saying regular polygons, but does it matter? No, it doesn't matter. It doesn't matter if a polygon's regular or not. You're still going to be able to find the same amount of triangles within a regular polygon versus one that's not regular, okay? Because right? If we go from one diagonal, sorry, if we create diagonals from one vertex to all the other vertices that it doesn't directly touch through the sides of the shape, we would have n minus 2 times by 180, right? N minus 2 triangles, that is here, okay? N minus 2 triangles, and then we'd have to multiply that by 180 degrees to figure out how much all the interior angles measured here. Okay, so that's how we translate the sum of the measures of the interior angles of a polygon. Boom, we just use the formula right there. Well, this is going to represent, we don't know how many sides this polygon has, so we're going to use n for that, use a variable. So the sum of the measures of the interior angles of a polygon, boom, we use the formula, okay, because this would determine, if we knew the amount of sides, this is what it's going to end up equaling once we plug in for n. We would just take away 2 from it and multiply it by 180. So that's what we have there. Okay, so I underline that because we have a formula for it. Then we get to a very helpful word right here. We get to the word is. Okay, gets the word is here. What does the word is mean in math when we change that to a word problem? Let's read this here. The sum of the measures of the interior angles of a polygon is 4 times the sum of the measures of its exterior angles. Well, the is thing is sort of connecting this part in green to this part here. I haven't underlined yet, but this is the second statement here. So is, what is means is an equal sign, okay, is an equal sign. That's one of the best words you can find within a word problem to help you start setting up an equation. So because I see is right here, I'm going to put an equal sign down. And to the left of the is, I had that n minus 2 and the 180 right here, okay, because the sum of the measures of the interiors of the polygon is equal to, right? Is implies is equal to. It says is equal to, it doesn't say equal to, but that's what it means, is equal to 4 times the sum of the measures of the interior angles. So here we have 4 times. So I'm going to write this 4 times, right? We're going to multiply 4 to something, 4 times. And then it says the sum of the measures of its exterior angles. What is the sum of the measures of the exterior angles of any convex polygon? One angle at each vertex, so one set of exterior angles. What is that other theorem that we have? We have this theorem for the interior angles. What's the other theorem for the exterior angles? It's always going to be 360, okay? So here we have 360. So here we have 4 times by 360, right? 4 times by 360, and that goes on the right side of the equation. Boom, there you have it. That's how we set up a word problem in problems like this, okay? Read them, find the formula, put it in, is equal sign, right? If you have is equal sign, and then if there's anything happening in formulas like here, it says we've got a 4 times the formula, or 4 times what we know from the theorem, so 4 times 360, and that's gonna be the right side of the equation, okay? That's the big thing. I have the rest of the solution up here in case you wanna look at it, in case you want to practice the algebra steps it would take. So look at this. This is exactly what I just wrote down. This is sort of showing you the algebra steps and how to simplify and sum that. I can go over that with you too in office hours if you want to come to get help on that. All right, keeping moving on here. We got number 16. It says the measure. So we'll do this even quicker, right? Now that I've done a couple examples, I just take it. I'll do this much more fast here. All right, the measure of each interior angle of a regular polygon. I'm going to stop at that word is, because that word is nice. And actually, maybe I'll circle that word is. Okay, that word is means equal. So we're going to have an equality here. Right? This will be an equality math sentence. And then the left side of this says the measure of each angle of so it says each interior angle of a regular polygon. So the left side of the equation is talking about each angle, not the interior angle, sum each angle. So we got to remember, this is how we find the interior angle, what each interior angle measures on a regular polygon, right? We don't know how many sides it has, so it's an n-gon right now. So n minus 2 times by 180 is the formula for the interior angle sum. We don't care about the sum. We care about each angle of which there are n angles, okay? The amount of angles you have in a polygon, the convex polygon, is going to be the same number as the number of sides that polygon has, right? That polygon has here. So I'm going to do that n minus 2 over 180 over n is my left side of the equation. All right, and then right side of the equation says 8 times, okay? So I'm gonna do 8 times, what do we have to multiply by 8? We need something 8 times bigger on the right side. 8 times what? That of an exterior angle, okay? Exterior angle. So here we have a formula for exterior angles. This is an easier formula here. Remember, the whole exterior, one set, right? One set, which means one in each vertex, sums to 360, So we know that it's a regular, so that means a regular polygon. That means it's equiangular in addition to being equilateral. So if it's equiangular, then the number of sides, right? We just need to divide this 360 by the number of sides because that's the number of sides matches how many exterior angles there are, one in each vertex. Okay, so 360 over n, 8 times 360 over n is going to be my right side. So that's what I'm going to set up, 8 times by 360 over n, and that's what we have. Okay, very similar to the lesson we had the other day. I showed you how to solve something like this with n in the denominator. So I'm not going to go through that now for the sake of time, for the sake of your focus, but this is, okay, this is on the exit ticket explain sheet. Look, this is the exit ticket explain sheet. I do go through the steps. So study this. If you're not sure how to algebraically solve this, we need to practice some algebra, and that's fine, but just come to office hours, right? I can help you out, or just dial in, just go straight to CSF tutoring and get some help, okay? Because this is, time is precious this year. I don't have so much time to do this in person with you guys here. What in a normal year, like, let's practice algebra, solve this. I don't think we have time for that now. So please seek out help though if you need it. All right, number 17. Let's do number 17. It says make a sketch showing how to tile the floor using both squares and regular octagons. Okay, remember this from yesterday, tiling a floor? Well, let's see here. Why does, because look here, this is a graph paper. This is a graph paper. This is actually a really good example. This graph paper is tiled, right? Meaning we're filling up all the space on the plane, or all the surface on the plane. Remember, planes are an infinite surface. We're filling up all the surface on the plane with squares here on a grid line. So check it out here. The reason, why does this work? Why are we allowed to, maybe I'll do this here, have a square here, and another square here, and then another square here, and then another square here. So we're allowed to fill up all the space, okay? We're allowed to fill up all the space, right? We can tile this using squares only, and we can just keep, we can just keep going with squares, and we filled up all the space, okay? The key to the reason why we're able to do that, this is sort of a review from homework review yesterday, is, for instance, like these are the 4 we initially started with here, 1, 2, 3, 4. They fill up all the space around this given point. Remember, that's how I actually set this one up, okay? I had a given point potentially, and I know I can tile it because I can fill up all the space with just the squares around that point, 1, 2, 3, and 4. Why am I able to do that with squares? How do squares help me? How do squares help me? Okay, let's maybe dive a little deeper into this here. Why do squares help me? Okay, well, the key to this, it turns out, right, the reason why we're able to tile something is actually a geometric calculation, figuring out what shapes you can actually tile a surface with. If you want to do a cool drawing of shapes that are all fitting in, filling the whole page, the whole surface you're working on here, this calculation can help you. If you're redesigning your house, right, and you want to use certain shapes, like I got tiles back there that are my backsplash, beautiful backsplash, if you don't mind me saying, gorgeous backsplash. They're all squares, right? It's tiled there. Hexagons, you see tiling a lot, right? The honeycomb design. I'm familiar with the honeycomb design, but there's a reason why a honeycomb works, right? Honeycomb works in terms of filling up an entire surface. Penny tiles, not so much. You need a lot of grout for those. That's not too good. I want to minimize your grout. So anyways, around this point, the reason why this works is, well, this point, we need to fill up how much of the surface around the point, right? We need to fill up all the surface around the point. So how much is that? So if we're talking about going around a point right here, how many degrees work? Because this connects to, right, again, this is called the angles of a polygon. This connects to the fact that angles of this polygon add to what? 360 degrees, right? If we get things that can add up, right, sum up to 360 degrees. So if I have just squares only, I can tile that. Because when I put 4 squares together at a common vertex, I get 360 degrees, right? 90 degrees times by 4 squares would equal 360 degrees. So I filled up all the surface that was available to be filled up around a given point. That's how tiling works. So let's check out this one here. It says, make a sketch to show how tile a floor using both squares and regular octagons. I don't think I can do octagons. Oh, no, I can actually do octagons in this tool. So let's see here. It says polygon. I'm going to do this. I'm going to do 8. Okay, let's see if we can do this here. Tile this up. Okay, there's an octagon. And it's regular, like equiangular and equilateral. So that will be my octagon. Let me see if I got pasted. So you got to kind of work around with this one here. We got this one. So this isn't tiling. This is going over. Oop, yep. Well, I'm going to do that. Make sure it's regular. Is it regular yet? Nope. Hold on. Copy, paste. Oh, paste. There we go. Okay. All right. Now, how do I move this? Teacher's like, how do I do this technology? Oh, there we go. Okay. So let's move this here maybe. I think I see it. So this is a common design, isn't it? Where have you seen a design like this before? Check it out. Boom, and boom. There you have it. Gorgeous, if you don't mind me saying. That's a gorgeous design. It's a very common design that you see in flooring. You'll never look at your bathroom floor again if it's this design. The same way again is what I meant to say. You'll definitely look at it again. You look at it all the time. You look at it more now. Now that we're talking about tiling, baby. Tiling, design. This is what it's all about, right? The magic of math behind some of human beings' greatest instincts, which is how do we make the world more beautiful around us? Well, we can use something called tessellation to our benefit, and we can tile it up. So this is it. Guys, this is the problem. You fast forwarding ahead? I don't know if you're fast forwarding ahead or not. Check it out. Boom. There you go here. Yeah, and you just repeat, rinse and repeat. And that's it. Just keep going again and again and again. And you see it? I can keep going and keep going out this way if I want to. Boom. And we're gonna just keep tiling this guy. Said something inappropriate there. So, anyways, there you have it. It says make a sketch, and that's all you got to do. You got to make a sketch. So let's see here if I can just really highlight it down. Like here we have octagon, 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 and here we have our, oh, in case you missed it, there's our square. There's our square. So pretty cool design, right? Pretty cool design. I got to get in the flooring game. And what am I doing wasting my time as a math teacher? I should be a contractor, a general contractor, build people's bathrooms, get paid good money. Man, it's expensive to redo your house. It's pretty expensive. Anyways, reason why this works though, don't ask you for the reason, but you might as well go. If I asked you, my friend, you should know by now. Reason why we can do this with both squares and regular octagons, and that's because a regular octagon has 135 degree. That's where it comes into it. Like it's helpful to actually memorize these things to hear that they've come up before, right? And be like, oh, okay, I'm not making mistakes. So I could have done that n minus 2 times by 180. So 8 is 8. So it would be 6 times 180, which would be 1080, right? 1080 divided by 8, 1080 divided by 8 would be 135. You can check on your calculator if you want to. But that's 135 degrees. This is 135 degrees right here. Okay, right? This is 135 degrees. This is 135 degrees. And then we have a 90-degree angle right there. So if we're talking about what the common vertex is as we're tiling these shapes with one another and tessellating the surface, this is called tessellation, something that you normally try to study in chapter 11, but we're not going to get that far, let's be honest here. So you have 135 degrees plus another 135 degrees plus 90 degrees. Check that out here, okay? And what's 135 plus 135 or 135 times 2? That's another thing you should quickly memorize. You have to do that a lot with these calculations we have here, right? 135 times 2 would be 270. And then 270 plus 90, well, 270 plus 100 would be 370. Take away 10, 360. Look at that, 360 degrees. It adds up to around that given point. And that's true right here. Look, we have an octagon, and we have a square, right? And we have a square tessellated. We're good to go. We're good to go at each vertex. So neat little design here. Octagons and squares tessellated with one another. They tile. Like it's pretty cool. Reason is because at each vertex, what am I doing? Using my keypad for this here. At each vertex, 2 octagons, 135 degree interior angles each, and 1 square, 90 degree interior angle. So at each vertex we have that. So the 3 shapes angles add to 360 degrees, which fills all surface around the common vertex of the shapes. Okay, sorry that's so hard to read, but I might ask you to kind of justify why that works at some point in time. So maybe rewatch that if you have questions about that. Okie dokie, getting to more algebra stuff here. Number 22, check this one out. Pretty sweet. A lot of algebra solving on this homework right here. We got quadrilateral ABCD. So again, some people said like reflection. Now you know who you are if you're the ones who said this. And I actually really appreciate that you said this here. Sometimes it's helpful to do some of these problems by just like underlining where it starts and then thinking about what you're being asked later. So this says quadrilateral ABCD. We know that that's going to have 360 degrees interior angle sum, okay? Interior angle sum. So I'm just doing that now. That might come into helpful later. Anyways, we have measure of angle A is x degrees. Measure of angle B is twice that, so it's 2x degrees. Measure of angle C is 3x, and measure of angle D is 4x. Find the value of x. Oh, there we go. And state which pair of sides of ABCD must be parallel, okay? Easy part's going to be the first part, okay? Easy part's going to be this one. Find the value of x. That's pretty easy because we know that the interior angle sum of a quadrilateral sums to 360. So what we got to do with that is we got to sum all the angles. Measure of angle A plus measure of angle B plus measure of angle C plus measure of angle D would have to equal 360 because it's a quadrilateral, darn it. And quadrilateral's interior angle sum is always 360, right? Any quadrilateral like this crazy looking one, right? We just make two triangles. It'll be 180 and 180 right here. So this guy right here, this quadrilateral sums to 360 degrees, okay? The interior angle sum, these 1, 2, 3, 4. Anywho, that's not going to be the diagram of this one. We'll have some parallel lines in a second. So we got to sum all the measures of the four angles here. The nice thing is those four angles were given variables to represent their measures. So x plus 2x plus, and C is 3x, and measure of angle D is 4x, and that's going to get us to 360. So this is a pretty simple problem to solve here. Got to combine like terms. So we have 1x here, another 2x, so that brings us to 3x, another 3x, that brings us to 6x, and 4 more x, that's 10x. And that's equal to 360. Just got to divide by 10, so x equals 36. All right, x equals 36. That's the first part of the problem. Don't forget, there's a second part of the problem. Lots of, once I get x, I'm done, right? No, you go back, my friends. You go back and you realize it says then state which pair of sides of angle of quadrilateral ABCD must be parallel. How do I get lines parallel to one another? How do I prove? How am I going to know this? We got to think about this, okay? I got to think about this. So remember, ABCD, okay? ABCD, this is it, right? Angle A is going to be, the next angle is going to be measure of angle B. The next angle is going to be measure of angle C. And the next angle is going to be measure of angle D. Remember, their names, quadrilaterals, polygons are named by naming the consecutive vertices, okay? Consecutive vertices. So, for instance, this could have been ABCD, quadrilateral ABCD, but this is not quadrilateral ABC. This is quadrilateral ACBD, right? BD. So it's got to be in order. It's got to be in order, okay? Right? So this could be that, but we don't know if it is based on the measurements here, but it could be. Okay, let's see here. All right, so anyways, measure of angle A is x, so that's 36 degrees. Measure of angle B is 2x, that's 72 degrees. Measure of angle C is 3x, so that's 108 degrees. Measure of angle D is 4x, so that's 144 degrees. What is wrong with me there? 144 degrees, okay? What do we notice here? What do we notice? How do we prove lines parallel? What are some ways we prove lines parallel? Well, let's just do a generic sketch. Quadrilateral. I'm trying to figure out what we're dealing with here. It's definitely not a quadrilateral. Let's undo this here. Well, how we prove that any of these angles are, we can find corresponding angles. Well, these are the four angles right here, right? What's sort of our reason here, okay? Yes. I think I heard you. So the only way to do this, the only angle relationships that we really have here are same side interior angles. So we got to figure out, these are all same side interior angles, right? These are all same side interior angles because they're consecutive to one another. Okay, they're consecutive to one another, right? Angle A and angle B, right, might be this. Okay, because they're consecutive. This is C and D. So BC are also same side interior angles. This is our transversal. These are the two lines. D and C are same side interior angles. These are the two lines. This is the transversal. So the question is, which one of these are supplementary? Because if same side interior angles are supplementary, then the lines are congruent. Sorry, lines are parallel, right? Are parallel. When two lines are cut by a transversal and same side interior angles are supplementary, then you've proven lines are parallel. So I think what's going to give us our answer here is, my friends, this, okay, this here. So angle B is supplementary angles, okay? Therefore, right? So let's look at our diagram here. This is B and this is C. These are supplementary according to the numbers here. Again, this is just a generic stretch. So the question is, what are the parallel lines? Okay, what are the parallel lines? Well, this is B and C. They're same side. So this has got to be the transversal because, right? BC is the transversal because these two angles are on the same side of the transversal here, okay? What are the two lines that got cut? Again, this is a generic, so it doesn't look like they're parallel. No, it is not. Generic diagram here, that means that these two lines must be parallel to one another because they're the same side interior angles are supplementary according to the numbers. Again, we're not looking at diagrams, we're looking at the numbers here. So B and C are supplementary angles. That means that AB, right? AB is parallel to CD. Okay, parallel to CD. So those are the parallel sides here. Okay, and there we have it. There we have it. Right, and then they named this intentionally here so that it's clear that B and C are same side interior angles. It's clear that C connects to D, and B connects to A. So that's how I know that my answer is right. Anyways, so I had a second question for a second, but I'm 100% sure this one's correct now. Okie dokie, go ahead and email me if you have any questions. I thought this was helpful. There's really one other B-level problem that I haven't even shown you yet. So anyways, good times. I have fun doing these problems. Hopefully you have fun doing them too. I know that some of them can be kind of more tricky, but again, it's a learning process. You're a student. It's your job, right? You're trying to get caught up in this stuff and try to be as effective as possible, right? Not everybody gets there. I hope you do, right? I hope you keep pushing yourself here. Take care, guys. Email if you have any questions or message, and we'll see you guys tomorrow. Halloween weekend coming up. It's going to be great. Bye.